My name is Charles Balin. I'm a professor of astronomy and physics here at Yale. I'm also the director of undergraduate studies in astronomy. And today it's my great pleasure to introduce the third of this year's Terry Lectures. Now, I have to confess that those of us who teach astronomy have a kind of ongoing low-level embarrassment. And this is the fact that what we want to teach our students is not the same thing as what our students want to learn from us. And in the topic of cosmology, for example, we're very comfortable talking about the 2- and 3-point correlation function of galaxies, about the power spectrum of perturbations in the cosmic microwave background, and about the possibility of observing baryon acoustic oscillations in large-scale surveys of the sky. But for some reason, our students don't ask us those questions. Rather, they ask us questions of the type, what happened before the Big Bang? Where is the edge of the universe? And what lies beyond it? And to these kinds of questions, we kind of smile nervously and try and retract the conversation back to something we're more comfortable with. So there is this kind of gap between what we think we know and what our students and our colleagues in other fields and the public wishes we knew. Into this gap have boldly gone Joel R. Premack and Nancy Ellen Abrams, our speakers for this set of Terry Lectures. Joel Premack is a distinguished astrophysicist who has made major contributions to the understanding of dark matter and how dark matter influences cosmic structure. Nancy Ellen Abrams can only be described as a polymath. She's a philosopher, she's an attorney with a specialty in conflict resolution, she's a musician, and many other things. And together, they have gone where the rest of us dare not, and have attempted to address the really big questions. And today is the third of their 4 lectures, and they'll be talking about, as I understand it, they'll be talking about this cosmically pivotal moment, which I assume turns out to be now. Thank you very much, and Nancy and Joel, we look forward to hearing you.
Thank you, Charles. It's always hard to be the third person to introduce the same people, so that was really very creative. Well, welcome to the third lecture, this cosmically pivotal moment. A moment is cosmically pivotal when the direction of the very long-term future hinges on what happens in that moment. And how likely is it that today really is a pivotal moment? The probability seems almost zero that in a 14-billion-year-old universe, anything should be special about the vanishingly small window of 21st century Earth. So perhaps claiming that today is cosmically pivotal seems grandiose nonsense. But let me suggest, don't look at the probability, look at the evidence. The first thing we're going to do in this lecture is to outline how we are in fact living at a pivotal moment, not only from the point of view of humanity, but of the Earth, the solar system, and the universe. Then we'll explore what the pivotal nature of this moment may mean and why it matters for all major political decisions being made today. Intentionally changing the course of post-industrial civilization has never been done before. But we believe that a cosmic society could do it. Joel and I are not arguing to use cosmology directly to reach better policy decisions. What we're advocating is to use cosmology to develop an encompassing understanding of our planet, a new awareness of the cosmic context surrounding and, to some extent, controlling global human affairs and the human-Earth relationship. Now, in Lecture 1, we showed that the way people look at their cosmos is reflected in the way that they see their own culture. And if their cosmos is narrow and largely fictitious, their perspective on everything is narrow and largely fictitious. This is part of our problem today. We showed in Lecture 1 that there's actually a largest and a smallest possible size permitted by the laws of physics, and they may be linked. We symbolized this with the cosmic Ouroboros, a serpent swallowing its tail. And in this finite but vast range of sizes, it turns out that we human beings, we intelligent beings, are central and we couldn't be anywhere else. Our nature arises from the nature of the universe. In Lecture 2, we showed that although we and everything we see, including the entire Earth, are made of atoms, all the atoms except hydrogen and helium are actually very rare. And even hydrogen and helium make up only a small fraction of the cosmic density. Most of the universe is made of dark matter and dark energy, whose dynamic interactions since the beginning of the universe have shaped the galaxies, which are the only possible homes where life could have evolved. So we are made of the rarest material in the universe, but our existence is supported by a massive pyramid of invisible matter and energy. In Lecture 2, we also explained that, like all observers, we are at the center of our cosmic horizon. We're surrounded by cosmic spheres of time, since as we look out into space, we're looking back in time, and we're receiving radiation from all of these previous cosmic epochs. Now, in this lecture, we will focus on the pivotal nature of this moment in time because it turns out that by understanding the newly discovered larger universe, we acquire new concepts that could give us the perspective we need to understand how our technologies are already having effects on the planetary and cosmic timescales. But without these new cosmological concepts, it will be very difficult to get a mental grasp on what we humans have to do to preserve ourselves and all of our potential. First, we have to start thinking cosmically about time. That is, time on the scale of the cosmos. The ability to think this way is new to our species. Politicians certainly aren't using it yet, and in our daily lives, it hasn't seemed necessary to think much further into the future than next year or when the kids go to college or the family legacy. But this has to change, and it can. Let's look briefly at how people's ideas of time have changed in the past. For millennia, it was assumed in the West, as Genesis implies, that human beings like us have been on the earth for its entire existence except for the first 5 days. Then, in the 19th century, the science of geology took off, and scientists tried to understand how mountains and river deltas formed. They were shocked to discover that some formations must have taken hundreds of millions of years. This was the beginning of the discovery of deep time. Throughout the 19th century, as excavation for railroads occurred across England and the United States, dinosaur bones and other fossils were uncovered, and the realization dawned on people that countless entire species had gone extinct long ago. By the mid-20th century, scientists using radioactivity determined that the Earth and the solar system itself are far older still, 4.6 billion years old. Compared to this vast age, we humans just evolved this morning, and we have appeared at a very particular moment, the midpoint of time.
What does it mean to call this the midpoint of time? Well, as I'll explain, we live at the peak moment in the history of the universe for astronomical observation. This is also the middle of the existence of our solar system. It's the midpoint of time for the evolution of complex life on Earth, and it's the end of the exponential expansion of the human impact on Earth. Let's start with the first one. Now is the peak moment in the lifetime of the universe for astronomical observation. There will never again be so many galaxies visible as there are in this ultra-deep field from the Hubble Space Telescope. How is this possible? Well, all distant galaxies are moving away from our Milky Way, and the farther away a galaxy is located, the faster it's moving away. Because the expansion of the universe is now accelerating, the most distant galaxies are beginning to disappear over the cosmic horizon. Meanwhile, in about 5 billion years, our own Milky Way will merge with the great galaxy in Andromeda, and many of the satellite galaxies will also merge. And this will form one big galaxy that we might call Milky Andromeda. Let's look at what that might look like. So I'm going to show you a video that my team made. It represents a merger between galaxies like the Milky Way and the Andromeda galaxy. These are realistic color images. Galaxy mergers like this one trigger gigantic starbursts, forming many millions of new stars, which look blue in the resulting images. But dust, which appears orange or brown in these images, absorbs up to 90% of the light, especially when new stars are being formed, and this energy is re-radiated in invisible long wavelengths. What we're going to show is just what these galaxies would look like to Hubble Space Telescope. So there's one galaxy, say ours, and now we'll set it going toward this other galaxy, say Andromeda. As the galaxies pass each other, their gravitational interaction triggers a gigantic starburst. Look at all those newly formed stars in blue. Gravity's pulling them back together. Their centers merge. And now the stars that surrounded these galaxies in a disk form a giant ball of stars, an elliptical galaxy. The whole process takes about 2 billion years. It's now finished, and we're moving the camera around the elliptical galaxy. There's a big dust lane about to across our field of view. And we see these in elliptical galaxies that we see in telescopes. Incidentally, when galaxies merge, almost no stars collide because stars are so tiny compared to the immense spaces between them. Far in the future, Milky Andromeda will be all that's visible to anyone living inside it, and it will be impossible forevermore to see any other galaxies. It took billions of years of cosmic evolution to build up the stardust required for Earth-like planets, and then billions of years of biological evolution on Earth for creatures to evolve with the technological capability to see the distant galaxies. So such observations couldn't have happened much sooner than now. Thus, this is the peak moment in the history of the universe for astronomical observation, as I said before. There will never again be so many galaxies visible. So we astronomers are telling the funding agencies, fund us quick. Closer to home, we're living in the middle of the existence of our solar system. In about 6 billion years, the evolving sun will puff up into a red giant star that will swallow the inner planets of Mercury and Venus and possibly burn Earth to a crisp. Since, as I mentioned, the solar system is now about 4.5 billion years old, this means that we're close to the middle of the roughly 10 billion year lifetime of a star like our sun. Third, on Earth, we're living at the midpoint of time for the evolution of complex life. This is the middle of the approximately 1 billion year lush and habitable period of Earth's existence when it has an oxygen-rich atmosphere and lots of water. The age of animals began about 500 million years ago with the so-called Cambrian explosion, when microorganisms increased the oxygen content of the atmosphere to nearly its present level, and the large animals started to evolve. In another 500 million years or so, the increasing heat output of the sun will evaporate the oceans, and the sun's ultraviolet light will dissociate water vapor at the top of the atmosphere, and most of the hydrogen will be permanently lost. Earth would then become a dune planet. Some of you may remember the science fiction novel. But don't worry. The sun will provide Earth with a perfectly livable amount of heat and light for at least several 100 million years, an almost unimaginably long time. Plus, as the sun heats up, our descendants will have plenty of time, millions of generations, to move to another suitable planetary system or move Earth farther from the sun. A way this could be done is by changing the orbits of large comets to borrow energy from Jupiter and transfer it to Earth. Every 100,000 years or so, our distant descendants would need to do this. No rush. Carefully, of course. The fourth way that we're living at the midpoint of time is that this is a pivotal moment for humanity. Our collective behavior is mirroring the greatest pivot point in the history of the universe, the beginning. First, let me explain what may have happened in this earliest instant of the Big Bang, and then we'll get to the way humanity today is mirroring that instant. There is substantial scientific evidence that a brief period called cosmic inflation may be what set up the initial conditions for the Big Bang. Cosmic inflation caused the universe to expand exponentially, doubling in size again and again, incredibly fast. This makes the universe have a very Euclidean or flat geometry, as observed. In that fraction of a second of cosmic inflation, the universe expanded from close to the Planck length all the way up to the human scale. That's just as much in powers of 10 as it has in the 13.7 billion years since then. That's how fast exponential growth can be. That first part took almost no time. Quantum effects that were happening during that brief moment of cosmic inflation were then expanded exponentially. Then the exponential growth stopped, and those quantum effects froze into space-time in a unique pattern of wrinkles like the lines on your hand. Cosmic inflation creates exactly the sort of fluctuations, that is, small differences in the amount of stuff from place to place, that could grow with cold dark matter into the galaxy distribution that we saw in the videos in lectures 1 and 2. The great chains, clusters, and superclusters of galaxies along the filaments in the cosmic web. This expanding cosmic web was the blueprint for our universe. It was created during the brief inflationary period, and the entire universe since then has been built on it. Thus, the effects of the brief period of cosmic inflation can reverberate forever. This reverberation is, in some sense, our universe. All the interesting parts of the story, the growth of galaxies, of stars, of heavy elements, of planetary systems, life, and intelligence, happened after the brief exponential expansion of cosmic inflation. How reliable is the theory of cosmic inflation? It makes 6 key predictions, and thus far it's been possible to test 5 of them, and they've all been found to agree with observations. Cosmic inflation is furthermore the only theory known that sets up the proper initial conditions for the Big Bang. In addition, it appears compatible with our modern theories of particle physics. It's definitely a theory to be taken seriously. Now, here is how our collective behavior is mirroring the beginning of the universe. Humanity's recently been going through its own version of inflation, growing exponentially in population and in our impacts on the Earth. Exponential growth occurs whenever the rate of growth of something is proportional to the thing itself. Compound interest works like that. A certain time t is required for the amount to double. After twice that time, it doubles again. Another time t, double again. Let me illustrate this with hypothetical pond scum that can double each day. So the first day, little bit of pond scum. Day 2, twice as much. Day 3, another doubling. Day 4, doubles again. Day 5, starting to get serious. Day 6, half the pond is covered. Day 7, I hope you can appreciate that it's really been speeding up. There it's shown graphically. Now, in any finite environment, exponential growth like this has to stop. This is the history of the human population for the last 2,000 years, and it's been growing very rapidly, more or less exponentially, for the last 200 years. In 1800, there were about 1 billion people on Earth. In the past 2 centuries, the population has increased by a factor of 6. There were 2 doublings, a factor of 4, in the last 100 years alone. That can never happen again. In fact, population experts agree that the Earth cannot support even one more doubling of the human population. In biology, exponential growth occurs when a species gets into runaway reproduction. It overconsumes the resources of its environmental niche, and then there's an abrupt die-off. Thankfully, we humans now know enough to be able to foresee such dangers. Are we smarter than pond scum? There's been even faster exponential growth in our use of natural resources. So, although the population's increased by a factor of 6 in the last 200 years, the economic output has increased by a factor of 100. Our energy use by a factor of 30, our carbon dioxide production by a factor of 20, our mobility in kilometers per person per day worldwide by a factor of 1,000. The US and a few other countries are producing far more than our share of carbon dioxide. So this graph, this picture, shows that the United States and China are the only two countries that are producing a huge amount, over 5 million thousand, so 5 trillion tons of carbon dioxide per year. This shows the same graph, the same map, but now we're showing the per capita production. And there's no country that rivals the United States in per capita production of carbon dioxide.
But it's not just carbon dioxide that's the problem. As this figure shows, a typical person in the United States uses his or her weight in materials, fuel, and food every day. For everyone in the world to reach present US levels of consumption, as billions aspire to do, would, with present technology, require 4 more planet Earths. Increases in greenhouse gases are now causing worldwide climate changes, the effects of which we're already seeing in the form of record-breaking heat waves, melting of the polar ice caps. We're running out of fresh water in topsoil worldwide. We've destroyed more than half of the Earth's forests and wetlands. And we're appropriating for human consumption a large and increasing fraction of the biological productivity of the entire Earth. Our actions are killing not just individual organisms, but wiping out entire species at the greatest rate since the extinction of the dinosaurs and many other species from a meteor impact 65 million years ago. Clearly, we are already beginning to hit material limits. We need to figure out quickly how to transition out of this current period of worldwide inflationary growth in our impact on the planet, but to do so as gently and justly as possible. There is a strong parallel between the brief transition from cosmic inflation to steady expansion of the universe and the brief transition on planet Earth from human inflationary growth to sustainability. We're living through that transition right now. But by the time this kind of problem becomes obvious enough that everyone recognizes it and the detractors actually shut up, it's too late. And sometimes a cartoon will say it all. 1990, global warming doesn't exist. 1995, okay, it exists, but it isn't man-made. 2000, okay, so it's man-made, but its effects aren't all bad. 2005, its effects will be really bad, but not until after I'm dead. And it's not a funny cartoon. And we could even add 2010, how can I make money off the melting of the polar ice caps?
A little more detail on the production of carbon in the atmosphere. So this is a plot of all the different human sources of carbon emission. And the basic point I want you to appreciate is that a increase in a factor of 100 in industrial output in 200 years corresponds to doubling every 30 years. So I've overplotted in orange what it would look like to double every 30 years. And you see that certainly for the last 100 years, that's a pretty good representation of our increasing carbon and carbon dioxide production. Now, you'll notice that all of the greenhouse gases, carbon dioxide in red, methane in blue, nitrous oxide in black, for example, have shown just in the last few years this sudden jump. Notice the suppressed zero. Now, what you have to understand is that all this is the effect of that doubling every 30 years going down here. The human production was negligible before compared to the oscillations in the natural production. But then, about 20 years ago, the human production became comparable to the natural production, and then with our rapid increase, it's going up very, very fast. The amount of carbon dioxide in the atmosphere can be tracked precisely by simply looking at the contents of little bubbles of air in ice cores. And this is the record going back 800,000 years. This graph is from a recent report that the US government just put out a couple of months ago. You also can see that the carbon dioxide increase in the last 20 years has tracked rather well the overall increase in temperature, which has gone up by about 1 degree Fahrenheit in the last 50 years. Now the question is, where is it going to go, the carbon dioxide? It's about 390 parts per million today. Remember, it's never been above 300 parts per million for a long time. It's going to be somewhere between about 500 and 900 or 1,000 parts per million in about 100 years. The consequences for climate are going to be pretty severe, as I'm going to explain in a few minutes.
In his election night victory speech, then President-elect Obama told the story of a 106-year-old voter named Ann Nixon Cooper, whom he had met, and he described the momentous changes that have happened in the United States during her lifetime. Let's watch that.
America, we have come so far. We have seen so much, but there's so much more to do. So tonight, let us ask ourselves, if our children should live to see the next century, if my daughters should be so lucky to live as long as Ann Nixon Cooper, what change will they see? What progress will we have made? This is our chance to answer that call. This is our moment. This is our time.
President Obama here has challenged the nation to think 100 years ahead to a time when his daughters, Malia and Sasha, might be as old as Ann Nixon Cooper. Well, let's call that time, the year 2108, the Malia-Sasha horizon. If our political leaders, business leaders, cultural leaders, and voters simply began today to consider as real the impacts of their own decisions just out to the Malia-Sasha horizon, this would be a giant first step in expanding our practical consciousness to cosmological time. The first step is the most important because it sets the direction and it overcomes inertia. In 1976, I was a young lawyer in the Congressional Office of Technology Assessment, which provided independent science advice to Congress. It was abolished after the Republican Revolution in 1994. My office already saw evidence in the 1970s that the Earth was warming, that cheap oil was running out, that our healthcare system was unsustainable. The job of my own section was to think about the long term, but the longest anyone ever thought about was 30 years. In Washington, where major decisions can be made with an eye to the current crisis or the next election, most people considered 30 years an absurdly luxurious and highly unrealistic timescale, and they didn't take it seriously. The result is that now those 30 years have passed, and every one of those problems has only gotten worse. Now we are running out of time. We can't continue this exponential growth rate of resource depletion and degradation of the atmosphere. But unfortunately, knowing this is not enough.
Now let me link this to the Malia-Sasha horizon. Here's some more graphs from that report I mentioned. In the 2007 Intergovernmental Panel on Climate Change report, they considered a number of different scenarios, and I want to focus here on two of them. Let's call them A and B. The B scenario is one of the most optimistic they considered, where the amount of carbon that's used peaks in about 2040, in 30 years, and then steadily declines. The A2 scenario is more or less business as usual, and the A1 even more so. And the amount of carbon keeps going up to the end of the century, the Malia-Sasha horizon. The consequence is that in B1, the atmospheric level of carbon dioxide, levels out at about 550 parts per million. Whereas in the A scenarios, it's around 900 parts per million by the Malia-Sasha horizon. The consequence, based on a whole suite of climate models, is that compared to the 1 degree since 1950 of average increase in global temperature, there's a 4-degree increase, that's 4 times as much by the Malia-Sasha horizon with the optimistic scenario, and about 7 or 8 times as much in these A scenarios. How are we doing now? Well, let's just look at the beginning of this projection. That's blown up here. And what you see is that the actual amount of carbon that we're putting into the atmosphere has been growing even faster than the pessimistic projections. Now, what are the consequences for the United States temperatures? This is the optimistic scenario, the B scenario. And, well, just to focus on Connecticut here, what you see is about a 2-degree temperature rise in 40 years, so double the increase since 1950. And by the end of the century, about a 4-degree temperature rise. In other words, 4 times the amount in the last 50 years. But now let's look at the pessimistic scenario, the A scenario. In 40 years, there's a factor of 4 increase locally, and by the end of the century, all across the country, even in Connecticut, it's about 8 degrees, 8 times the temperature rise since 1950. The consequences for climate are pretty drastic.
There's no question that we have to stop binging on carbon-based energy sources, but there are lots of questions about how best to do that. One of the big questions is the role of nuclear power. In the 1970s and 1980s, the dangers of nuclear power, combined with its huge expense, convinced many of us that nuclear was not a long-term solution. Even today, our country has not figured out how to dispose of nuclear waste in a way that will be safe for the tens of thousands of years that it will remain radioactive. These are major negatives for nuclear power. But, on the other hand, we have a potentially much bigger crisis on our hands. If humanity keeps pouring carbon into the atmosphere, the climate destabilizes, ocean currents change, and around the world there are extreme droughts, starvation, wildfires, floods, diseases spreading where they were never seen before, and countless climate refugees roaming the globe and fighting just for a place to live. So on second thought, if nuclear power could seriously help avoid this fate, we have to reconsider it with an open mind and ask, could it be made safe and economically competitive? How so, and which version would be best? But whom can we trust to answer these questions? Not the utilities, whose goal is their bottom line, but the relevant government agencies besieged by lobbyists and the media and juggling economic, political, and social pressures rarely have the ability to figure out what are the scientifically most responsible answers. I invented a method to deal with this kind of situation when I was working at the Office of Technology Assessment. It's called scientific mediation. It's never been attempted in the United States, to my knowledge, but it was very successful when the Swedish government used it to help determine if their utilities plan for nuclear waste disposal was adequate. The result was so illuminating that scientific mediation became standard procedure in the Swedish Ministry of Industry. So let me briefly explain it. To do a scientific mediation, a government agency basically only needs 3 people: one well-respected expert scientist on each side, and a mediator. I played the role of the mediator in Sweden. Each scientist believes that the existing data favors his or her position. With the help of the mediator, the opposing scientists must collaborate on a joint report in which they do three things. First, they have to list the main points of disagreement. Second, they have to state the arguments not only for their own side, but for the other side until they satisfy their opponent that they understand his or her position. And third, which is the most illuminating part, they have to agree on why they disagree, point for point. They never agree on scientific questions that they disagree on, but they agree on why they disagree. Then both of them sign the final document. Scientists and other expert advisors to government are human beings like everybody else. They can mix personal biases into their official positions, sometimes without even realizing that they're doing it. But during this unusual procedure of scientific mediation, those biases surface, and it becomes clear which of their policy recommendations, if any, are truly based on science. When their report is made public, anyone can understand the dispute and what is at stake, far better, in fact, than the scientists themselves did at the beginning. If some government agency or foundation sponsored a real scientific mediation on the question of whether nuclear power could be made safe, or any fundamental scientific question underlying a current policy dispute, we, the people, would come out of it with the best understanding possible at this time, and one that would be fair to all sides. That alone would be invaluable. What the country decides to do about it, well, let's battle it out. That's what politics is for, and a cosmic society will still be a political society. But let's first demand that all options being fought over are grounded in reality. We're looking for a shareable picture of reality that's based on science and from which we can proceed to plan our future. Thank you. Cosmology is not necessary to diagnose our global predicament. Many people see it, but cosmology could help us see the way out. The universe's inflationary period ended with a big bang, but this was good. Only after inflation did the universe enter its most creative and long-lived phase. Evolution takes time. The fundamental character of the universe has been to grow in complexity, and this could be our future too. That pivotal moment when the universe transitioned from exponentially explosive growth to slow expansion could become a model for how to think about the transition to sustainability that we humans are about to make. Let me be more precise. Like the quantum fluctuations that froze into wrinkles in space-time when inflation suddenly stopped, political and social decisions made during these final years of human inflationary growth may end up getting frozen into the future of our species and our planet. Nothing could be less useful than to think that politics doesn't matter. Today's actions and failures to act may reverberate into the distant future far out of proportion to the thought that's going into them. On the plus side, there are many fine people genuinely trying to save the Earth, but they often assume that the only solution is that growth of population and resource use must stop and then decrease. But if we take the universe as our model, we notice that at the end of cosmic inflation, the universe did not, in fact, stop dead like a truck hitting a brick wall. The exponential rate of growth stopped, but not growth itself. The universe essentially slammed on the brakes, slowed to a crawl, and kept going for the next 14 billion years. Inflationary growth that is transformed to slow but steady expansion can go on for billions of years. For us, this means that the end of exponential growth, which is approaching, is like the end of adolescence. It's a coming of age. And from then on, the growth of complexity in human civilization won't be physical anymore, but intellectual, emotional, artistic, relational, and spiritual. In this age of electronics and information, it should be possible for humanity to achieve sustainable prosperity without profligate resource use. In fact, only without it. If we take the universe as our model, we should plan for and seek a stable period in resource use, which can only happen with renewables. The universe, of course, made this shift naturally. For it, injustice, suffering, addiction, fatalism did not have to be overcome because they didn't exist. But for us, they do. Nevertheless, we have the knowledge and the internal resources to overcome them. Only resource-heavy activities have to slow down. Our drive for meaning, spiritual connection, personal expression, and cultural growth can be unlimited. If those were valued above consumer goods, which they tend to be only after people lose them, then we would have a new paradigm for human progress. For our universe, the most creative period came after inflation ended, and this could also be true for humanity. A stable period can last as long as our creativity stays ahead of our physical impact on the Earth. The key to sustainability is to find the ideal growth rate that allows human ingenuity to stay just ahead of resource use by foreseeing and minimizing consequences. People sometimes assume that to maintain a stable environment, innovation must be suppressed, but the opposite is the truth. Nonstop creativity will be essential to maintain long-term stability. Those of us who are alive today, and especially you who are young, will determine whether this happens or not. Either way is a huge choice that will determine the character, for better or worse, of the long-term future. This is what it means to be living at a cosmically pivotal moment.
I want to give you an example that pulls together in a rather practical way the idea that we're living at a pivotal moment with the idea from Lecture 1 that different ways of thinking are required on different size scales and time scales. In this example, you'll see a stark mismatch between today's very short-term economic and political thinking and potential long-term consequences for the entire planet and future generations. Destruction of the space environment by space debris is the problem, and Nancy and I have been working for years to try to solve it. In 1988, Nancy and I traveled to the old Soviet Union in a collaborative effort of American and Soviet scientists and international lawyers. We were trying to end the practice of launching nuclear reactors into orbit to power satellites. I want to emphasize that I'm talking about nuclear reactors with a minimum of 50 kilograms of high-enriched uranium, not plutonium power packs. Those reactors would eventually become radioactive space debris. The USSR had already launched about 40 of them, and 2 had fallen back to Earth, one of them contaminating a 200-mile swath of northern Canada with radiation. This shows the orbits of the nuclear reactor-powered satellites, and this was part of the cleanup operation after one of them fell back to Earth in 1978 over northern Canada. This is from a Scientific American article my colleagues and I, Russian and American, published back in 1991. The US, meanwhile, was planning to launch much bigger nuclear reactors to power missile defense, popularly known as Star Wars. And we thought the USSR might be willing to stop their reactor launching program if the US would not start. Actually, I should explain. The US launched the first of these nuclear reactor-powered satellites. We actually got the Soviet government to agree not to launch any new reactors for 2 years. But by the end of 2 years, the Soviet Union had ceased to exist, and no more nuclear reactors have ever been launched into space. Many people heard about the space debris issue for the first time on February 10th of this year, when an American communications satellite and a defunct Russian satellite, moving in different orbits at about 17,000 miles per hour, crashed into each other and broke up into countless pieces. When that kind of thing happens, it's not like the science fiction movies where there are big explosions and then space clears. In this scene from the first Star Wars movie, on the left, you see a big explosion in space near a planet. And then, a moment later, the pieces disappear and the view from the cockpit is perfectly clear. What really happens in a collision in space is that some pieces fall toward Earth and burn up in the atmosphere, but the rest go into erratic orbits. They move at speeds 10 times faster than a high-powered rifle bullet. As the number of satellites and pieces of satellites at a given altitude increases, eventually a chain reaction begins. With enough orbiting debris, pieces begin to hit other pieces, smashing them into fragments, which will in turn hit more pieces. The process may already have begun. Over 10,000 pieces larger than 10 centimeters in size are now tracked. But countless smaller ones are not tracked. No one knows exactly where they are. This is a blow-up of the region right near the Earth. And this happens to be the situation at one particular moment on May 7th of this year. I got this from NASA. This issue matters because space is our most fragile environment. It has the least ability to repair itself. Only the Earth's atmosphere can remove satellites from orbit. When the sun flares up in its 11-year cycle, it heats the upper atmosphere and makes it expand so that debris and spacecraft in low orbits are subjected to increased drag and start to come down. But the higher the original orbit, the less air, and high enough debris, there's nothing to stop them and bring them down. Terrible as they are, millions of landmines left over from earlier wars in Afghanistan and other countries can eventually be removed, but debris in orbit higher than 800 kilometers above the Earth's surface will be up there for decades, above 1,000 kilometers for centuries, above 1,500 kilometers, effectively forever. There's no known way to clean up space debris. Any bucket put up there to catch the pieces would itself just become debris.
When you realize how long a civilization humanity could have, and how much we have to do now to protect that future, you realize the importance of this issue. We're not going to want to give up satellites. If our future development is going to be based on improved cultural links rather than endless resource consumption, we have to protect our means of communication. We'll need satellites for a very long time, but we can't keep launching new ones indefinitely without bringing down the old ones. What are we thinking? Once we realize that we are at the midpoint of time, it becomes common sense, a new common sense, to insist that every satellite launched by anyone in the world have a rocket on it that allows it to be brought down safely. This can be done. Humanity only gets one chance to save space for all future generations, and now is it.
But accidental collisions of space debris are not the worst threat to the space environment. The worst threat is war in space. The public debate over Star Wars has gone on in the United States for a quarter of a century, since the Reagan years, and it's focused on the massive cost and unlikelihood that the system could work. But the debate has mostly missed the most crucial point. Even one war in space will create a battlefield that will last effectively forever, encasing our entire planet inside a shell of speeding metal shards. This will make space near Earth highly hazardous for peaceful as well as military purposes. No actual war in space even has to be fought to create this catastrophe. Preparation for it is enough, because any country that felt threatened by some other country's lasers or other weapons in space could launch the equivalent of gravel to destroy the sophisticated weaponry, and also destroy any civilian satellites at that altitude, like those we all depend on for weather information, global positioning, or communications. So here's a list of suggested space protection principles. Don't introduce attack weapons into space. Avoid fragmentation of satellites. Prohibit explosions of any kind in space. Require all satellites to re-enter when their useful life is over. Ban nuclear reactors in orbit. Minimize light pollution from orbit.
Political alliances are always shifting, sometimes drastically. Our deadliest enemies 65 years ago, the Germans and the Japanese, have been among our closest allies for decades already. It may seem that jazzy new weapons in space will give us a leg up over the arch enemy of the day, whoever that may be, but in making this choice, we actually become our own arch enemy. Any temporary military advantage would pale before the overwhelming, eternal immorality of imprisoning Earth for thousands of years in a halo of bullets, the most evil possible twist on the idea of a halo. No one can predict what the country will be like when Malia and Sasha are old, but we have a moral obligation to take into account the likely impacts of our own current decisions, at least out to the Malia-Sasha horizon, and we have an intellectual obligation to base those projections on solid science, which will require new approaches like scientific mediation to get that level of science into the policy-making process. How should we think about the long term? Some Native Americans have the concept of responsibility to the seventh generation, a wonderful impulse that actually I believe some paper towels have been named after. But the phrase is wrong for our time because it makes it sound as though every generation has the same responsibility. But we who are alive today have a far larger responsibility than earlier, less knowledgeable generations, or later, less pivotal generations. No one actually chose us for this responsibility. We just happen to be the ones living at what must be the end of human inflation. But the end result is that we and our children may be the most significant generations of humans that have yet lived. The real challenge of our time is to understand nature in order to harmonize our behavior with nature, not just to exploit nature technologically while generating heaps of garbage and unhappiness.
How important is it to take a cosmic view now? It turns out that the entire future of the visible universe may depend on what we 21st century humans collectively do at this moment of transition. That's not an overstatement, and here's why. We actually know something about the future of the universe. This is based on a computer simulation by some colleagues of mine, and this first big rectangle shows our own galaxy and some nearby galaxies. This whole region expands to an enormous size such that the little rectangle surrounding our galaxy becomes this big rectangle. And what you'll notice is that in 40 billion years, when this expansion has occurred, there's hardly anything in this whole region because of the exponential expansion of space. Another 40 billion years, now 78 billion years in the future, and that's it, that's our galaxy, actually Milky Andromeda, and nothing visible, just about out to the cosmic horizon. When the universe is twice its present age, most distant galaxies will have disappeared over the cosmic horizon. When Milky Andromeda has become, for our distant descendants, the entire visible universe, our descendants could have radiated life and intelligence throughout it. In short, our descendants could be the source of intelligence for the entire future visible universe. Alternatively, today's humans could keep thinking small, refuse to face reality, and over the next few decades destroy the necessary conditions for our kind of life to survive. The vast majority of Earth species have become extinct. There's no special dispensation for our branch of the primates. But the fate of other species is no excuse for giving up on our fate, and ourselves, because the very fact that we can understand this and discuss the options proves that we have the huge advantage of forethought.
There may be microbial life on many other worlds, but it took an outrageously improbable series of events on Earth, plus multiple cosmic catastrophes to earlier species like the dinosaurs, before we were able to evolve. Earth is our only example of the evolution of life. If these low probability events were essential, then our level of intelligence and higher may be extremely rare. Of course, we're all interested in discovering alien life out there, but we may actually be the only intelligence of our kind. Will there be consciousness and meaning in the future universe? Or will there just be sound and fury signifying nothing? That could be what's at stake in this cosmically pivotal moment. Several times I have heard people say, quite seriously, that Earth would be better off without humans because we're wrecking the environment. They claim that human extinction might not be such a bad thing. But from the point of view of the universe as a whole, intelligent life may be the rarest of all occurrences and the most in need of protection. We, and in this we I include all intelligent, self-aware creatures that may exist anywhere, we are the universe's only way of reflecting on itself. Together we are the consciousness of the universe. The entire universe is meaningless without us. I'm not saying the universe doesn't exist without intelligent beings. Something would exist, but it wouldn't be a universe, because a universe is an idea, and there would be no ideas. Earth's problem is not the presence of intelligence. It's that perhaps we're not intelligent enough yet to take a cosmic perspective. Our challenge is to break through and see the truest universe of our time, not just as physics, but as our shared mental homeland, a homeland where cosmological time is a normal perspective, and global threats that may not spin out of control for another generation are nevertheless as real as a hurricane that will hit your home tonight. Our challenge is to develop a cosmological vision that can be widely understood and shared irrespective of religion, and is grounded in scientific understanding of both the universe and human behavior, since our reality is an interaction of the two. A coherent, shared cosmology like this was for earlier cultures a source of bonding power that enabled people to cooperate in ever larger groups, and this is what made civilization possible. A global civilization will need to cooperate in much larger numbers. The rapidly growing countries like China and India must be included in this cooperation. Our scientific understanding of our human predicament may be the most important thing that we all have in common. Will we rise to these challenges? One thing is certain. If we create this vision, if we commit ourselves to implement it within the known laws of nature, and if in doing so we create a de facto community that supports and loves the vision, we will dramatically raise the probability that the answer will be yes. If we wake up to the reality of our universe and our predicament on Earth, if we humbly accept facts without letting ideologies suppress or distort them, if we become willing to expand our interpretations of our religious traditions to encompass new knowledge, if we integrate it into our thinking and eventually our dreaming and our art, then our culture will have a new enlightenment, and we will become a cosmic society. So think cosmically, act globally, eat locally. Thank you very much.